video, join with video.
Okay.
There you go. I just picked you to add and add with audio if that asks you that.
Okay.
All right, I think you're here. Yep, there you are.
Yeah, okay.
All right. All right, you made it.
Oh, okay. I hear you.
Okay, everyone. So I don't know what's up with LSR. We'll get started. I'm recording this. I'm telling you ahead of time. I'm recording it, and the main reason I'm recording it is so that if you're not here or you want to go back and look at the PowerPoints, because I didn't convert them to video, because I know the audio wasn't all that great. So I'm going to go through them. But if I can record it, then that gives it the option of going back and looking at it again later if you want. So I'll put it in the Edmodo. And then LSR, or if we're missing, like I was going to record it last time, but I paused it because we were trying to troubleshoot. And I forgot to turn it back on. So that's why I didn't have it for last week. So, let's, did you guys all look at the stuff from in Edmodo from last week that was up there?
Yeah.
Okay. All right, good. So I'm going to try and post documents because I'm not giving you handouts, but if they're there, you'll at least be able to go back and find them. Okay, and go back and reference them. So the game plan for today is to cover different types of motion, a little bit about cutter compensation, how we can control that. And then I have a little simple assignment that I'm going to want you to do, write a program, but I'm going to show you how you do that. And it kind of depends on our time. You know, if it takes longer than I think, then we'll have to get that next time. But I found a free website online that works just like the simulators at TMA, where you can enter a program and you can graphically look at it. So I thought that would be helpful. Oh, and speaking of that, I just got an email today from TMA. They're talking, they believe that we will be able to do our hands-on starting July 9th and then going for 6 Thursdays after that. So like July 9th to August 13th. I'm sure they're going to reach out to you. They just figured I'd throw it out there so that you could plan. So it's going to be those Thursdays, which was our normal lab night. We're going to have to, you know, because we're going to be together or whatever. I think the protocol is going to be a mask, and we're going to have to clean stuff. And so we'll get those details as we get closer. But I just wanted to let you know that that's kind of the plan for us to be able to finish up in July. Okay. I'm going to get rolling then. I'm going to share my screen, and I'm going to try and play one of these PowerPoints that's on the motions, because we have G00, G01, 2, and 3. Those are our main cutting motions, or rapid. And the PowerPoint does a fairly decent job. So let me share the screen and we will do that. If I can find it. All right, are you able to see that with the yellow?
Yeah.
Okay. All right, so let me know if I need to make it louder. You might have to do some adjusting, but it seemed to be working. I tested it with my wife's computer in the other room, and it seemed to work better than when I tried recording it. So this is about the 3 different types of motions, basically. Straight line, rapid, and circles.
you note that all machining centers have three linear axes, X, Y, and Z.
Were you able to hear that? All right.
Yeah.
Okay.
Here we're viewing a vertical machining center from above and removing the headstock to expose the tool that's actually doing the machining. Here we're positioning the tool and getting it ready to perform a machining operation. During this y-axis movement, don't you agree that since only the y-axis is moving, the motion can't help but be in the form of a perfectly straight line?
True.
The same is true for this x-axis movement. Again, only the x-axis is moving, so the motion has to be in the form of a straight line.
Is that big enough on your screen? Or should I try and make it bigger?
Big enough for me.
That's big enough for me.
Okay.
Yeah.
I know somebody's on a phone and that might be a little harder.
As is the case for this y-axis movement. Again, the motion is along a perfectly straight line. But notice that during this angular movement, both the x and y axes are moving. If this motion is to be along a perfectly straight line, the CNC control must articulate the motion. That is, it must move the x and y axes in a very precise and coordinated manner. In CNC terms, this kind of articulation is called interpolation. What's really going to happen here is that the control is going to cause the axes to move along a series of very tiny single-axis departures. They're stepping the axes in such a way that the desired motion is formed. Now, the resolution of these stair steps is very tiny, and you won't actually see any witness marks left on the workpiece caused by these stair steps. But you really must understand that this is what's going on whenever you're forming an angular motion. The control is interpolating the movement. That is, it's doing its best to provide the desired motion type. But you must understand that the motion won't be perfect. Note that the same kind of thing is going to happen with circular movements. Notice the stair-stepping effect that's going to occur during a circular motion command. Note that straight line motion and circular motion are commonly referred to as linear interpolation and circular interpolation. All CNC machining centers come with three basic motion types. And frankly speaking, the vast majority of workpieces can be handled with just these three motion types. This should be nice to know. Every movement you see a machining center make can be broken into one of these three motion types: rapid motion, linear motion, and circular motion. Here's an animation that should help you easily determine the difference between the motion types. All motion types share four things in common. First of all, they are all modal, meaning once a motion type is instated, it will remain in effect until it is changed. This means you need not include the motion command word in every command, at least not if you're continuing with that motion type.
So modal's a big thing, and if you're writing a manual program, it makes your life a whole lot easier that you don't have to put all that stuff. The only time I recommend repeating your X, your Y, your Z is if you're new at programming and you're doing manual. It helps you keep in check where you are. But once you kind of got a handle on it, there's really no need for it.
Second, every motion type requires that you include the end point for the motion. The CNC control will assume that the tool is already at the start point for the motion. So once again, you need only include the end point for each motion. Third, only the moving axes must be included in the motion command. If, for example, you're only moving the X and Y axes in a movement, you need not include a Z word. If the tool is only moving in Z, you need not include the X and Y words. If a tool is simply moving the X axis, you need not include the Y or Z words. While including redundant words really doesn't hurt, you'll notice that this Y position is the same as the most recent Y position. It does invite the potential for mistakes. You could write or type this word wrong. Redundant words also make the program longer, and we recommend leaving out those words that are not absolutely required.
Now, just a little note here, this line N20, if you remember last week, we talked about tool length offset, where it picks up the offset that's in the control for the tool length. This is that G43. H1's our height offset, and they're rapiding to 100 above the part and turning the coolant on. So that's always going to be your first move. Always has to have that G43, or else it's going to be a bad day.
And fourth, all motions can be commanded in either the absolute mode or the incremental mode. And from our previous discussions, you should know that the absolute mode should be your mode of choice.
Definitely. A little later, I'll show you when some programmers use incremental in here, and it's okay as long as you remember to go back to G90 absolute. Otherwise, it, again, creates a bad day.
Before you can actually command a tool's movement, you must, of course, know the point on the tool that you are actually programming. While it may seem like this is somewhat obvious, usually you must compensate for some portion of the tool while you're making motion commands. Here we're going to take a conscious look at the most common tools you'll be programming on machining centers. Let's start with hole machining tools. All hole machining tools that plunge a hole in the Z-axis require that you program the very center of the tool in the X and Y axes. This is usually quite easy for hole machining operations, since the centerline coordinates for each hole are commonly specified right on the print. You simply match the centerline of the spindle to that hole location. When programming a center drill, you'll be programming the very tip of the tool in the Z-axis. Note that the point length on center drills will vary based on the center drill size. All center drills will have a 60-degree included angle. Spot drills are commonly used to start a hole that's eventually going to be drilled. Since it has a 90-degree included angle, many programmers use spot drills to actually chamfer the subsequently drilled hole. That is, they spot drill to a depth that will be the chamfer size larger than the hole that will be eventually drilled. Calculating spot drill depth is quite easy, again, because the tool has a 90-degree included angle. Simply program the spot drill's depth as exactly half the diameter you're spot drilling.
And that makes it easy compared to like an 82 degrees center drill. 90 is the one to go with. Makes life easy.
You're also going to be programming the extreme tip or point of a twist drill. Twist drills have an included angle of 118 degrees. To calculate the lead of this kind of drill, simply multiply 0.3 times the drill diameter.
These formulas for like a different angle is in your Haas book on one of the pages I told you to earmark so that you can find those different formulas. If it's 150 degree or whatever the common ones are, they're in that formula, and it changes the, instead of 0.3, it's some other number times the diameter.
Countersinks are commonly used to chamfer holes after the hole has been machined. You'll be programming the extreme tip of the countersink, and countersinks have an 82-degree included angle. While you will be programming the extreme tip of any tap, determining how many imperfect threads can sometimes be difficult. There are several types of taps that have different amounts of imperfect threads. A bottoming tap, for example, might only have one imperfect thread, while a typical pulley tap might have as many as 3 or 4 imperfect threads. Again, you'll have to know the specific tap you're working with in order to determine how deep to tap holes. You'll also be programming the extreme end of any reamer. And do note that the lead of a reamer is commonly a chamfer on the outside diameter. Note that a true counterbore has a pilot that actually enters the hole that's been previously machined. And most experienced programmers would agree that you should be programming the cutting edge of the counterbore. This will ensure that the depth you program will be the depth of the counterbored hole. You must, of course, allow for the pilot of the counterbore as you make movements between holes. Note that if machining a counterbored hole in a flat surface, most programmers will simply use a center cutting end mill. This way they can avoid the clearance problems caused by the pilot.
And on the CNC machine, you don't need a pilot because you already have the accuracy of the location by the machine.
And finally, you'll be programming the extreme tip of any boring bar. As with most hole machining tools, you'll be programming the extreme tip of any milling cutter in the Z-axis. When it comes to the X and Y axes, the style of milling cutter being used and the kind of machining operation being performed determine what point on the tool you're actually programming. When face milling, for example, we recommend programming the centerline path of the face mill, meaning you'll be programming the centerline coordinates for the face mill in X and Y for all positioning movements.
Which means you might have to do some math to figure out where the center of that space is.
Most milling cutters are designed to machine on the periphery of the milling cutter, allowing contour milling operations to be performed. When milling on the periphery of the cutter, you can still specify centerline coordinates for the tool's path. But from a manual programmer's standpoint, this can make programming rather difficult. You must take into consideration the milling cutter's radius for every positioning movement. There is a feature we present in key concept number 4 called cutter radius compensation. One of the benefits of cutter radius compensation is that it allows a manual programmer to specify the tool path for contour milling operations right on the work surface. The manual programmer can ignore the size of the milling cutter being used to mill the contour. This makes calculating the coordinates needed for the milling cutter's path much easier. Note that we have not yet discussed cutter radius compensation, so with the examples coming up in this lesson, we're programming the tool's centerline path.
Now the tool centerline path, I used to do where we had to write a program for it, but it really doesn't make any sense because most people are going to use the cutter compensation or the cutter radius compensation because that allows me to use resharpened end mills. If I break an end mill and I don't have any more 1 inch, but I got a resharpened 1 inch that's now 975, I can just change my offset and correct the program.
Rapid motion is commanded by the word G00 or simply G0. When under the influence of a G00 motion command, the axes will move as fast as possible at the machine's rapid rate. Note that if 2 or more axes are commanded together, motion may not necessarily move along a perfectly straight line. With panic controls, all axes are turned loose to move at their rapid rates. And if one axis has less distance to travel in the motion command, it will reach its destination first. Rapid motion is used to minimize the cycle time in a program. We make the general statement that if the tool is not cutting anything, it should be rapiding.
And this, if you remember, I talked about this for the lathe. It goes, a rapid move goes at 45 degrees, and when it gets when it gets to the shortest axes, then it goes straight across and finish. So it makes it hard to calculate exactly the path that it's going to take.
Current model CNC machining centers have extremely fast rapid rates. There are some today that can rapid over 2,000 inches per minute. This can be very scary for a setup person when a tool is approaching the workpiece and it's only going to stop within 100 thousandths of the work surface. For this reason, all machine tool builders provide some way of allowing the setup person to take control of the rapid rate, slowing it down for the program's verification. One common switch is called the rapid override switch. This switch is like a rheostat and lets you take control of how fast the machine moves when in the rapid mode. And again, this is very helpful when verifying CNC programs. Here's the beginning of a program that stresses the use of the rapid mode for approaching a workpiece. After the program number and after we start the spindle, notice we position the tool first in X, second in Y, and third in Z. These approach movements are being made in the rapid mode. Admittedly, the single-axis approach movements made in the previous program are not very efficient. A better way to approach, and the way we recommend that beginners do, is to first move in X and Y, and then move in Z. In block number 10's approach movement in X and Y, notice that the Y-axis reaches its destination first, and the control continues on in the X-axis. You must be aware that this is how the control makes multi-axis rapid movements. All axes are simply cut loose to move as fast as they can. If you're trying to reduce cycle time to its bare minimum, remember that you can approach in all three axes simultaneously. If you do elect to do this, we urge you to keep the first Z-axis approach position at least 1 inch above all obstructions. Once the tool is in the XY position, then let the tool drop down the last inch or so in Z.
This XYZ move is one that your setup and your operators will hate you for if you're the program, especially when you zoom right to the tip top of the part, because you're not expecting it, and sometimes you have unexpected results because you can't control that 45-degree motion because it does it X, Y, and Z all at 45 until it satisfies. So it gets messy. So it's really preferred to up above after the tool change X, Y, then come down in Z.
Most programmers will rapid the tool to within 100 thousandths or 2.5 millimeters of the surface they're going to be machining. And for beginning programmers, this makes an excellent approach distance when you're approaching qualified surfaces, surfaces that aren't varying more than a few thousandths. But as you continue with your CNC programming career, you must understand that there is a direct relationship between cycle time and rapid approach distance. If, for example, you're going to be drilling 50 holes and you're using a 100 thousandths approach, this tool will be approaching for an overall travel distance of 5 inches. That's 5 inches of air cutting time. If, for example, you're using a feed rate for this tool of 5 inches per minute, that's going to equate to 1 minute of cycle time. If we reduce the rapid approach distance to 50 thousandths instead of 100 thousandths, we'll reduce the program's execution time by 30 seconds. Linear motion, which is also called straight line cutting motion, is commanded by G01 or G1. G01 will cause the control to do its best to give you a perfectly straight motion. G01 also requires a feed rate. And note that the feed rate is also modal, meaning once a feed rate is instated, it need not be specified in every command. The primary use for G01 is to allow the machining of straight surfaces. Note that some programmers, knowing that rapid motion is so very fast, will use G01 to fast feed approach.
Oh, I just want to mention real quick, we shouldn't have a problem. We didn't last week, but if for some reason Zoom boots me off, I'll email you a new link to carry on, okay? I don't expect to be a problem, but I just want to give you a heads up that I'm not blowing you off.
While most machining center users will never come close to requiring this fast a feed rate, it's nice to know that your maximum feed rate is usually about half the machine's rapid rate. If your machine has a rapid rate of 600 inches per minute, it's likely that your maximum feed rate will be about 300 inches per minute. Also note that while the machine is actually executing a CNC program, you have control of the programmed feed rate with a multi-position switch called feed rate override. With most machines, you'll be allowed to double the programmed feed rate, as well as to completely stop the motion with the feed rate override switch. The goal, of course, is to have your feed rates programmed properly, so the operator can keep the feed rate override switch at 100% for the entire program. Here is an example program that stresses the use of both the rapid and straight line cutting modes. We're using the G01 command in this program to drill holes. Here is another example program that uses G01 to mill a slot. Note that with this example program, we're also using G01 for a fast feed approach. While this movement hasn't actually cut anything, it's moving at a very fast feed rate. This gives the operator complete control of the final approach movement with feed rate override. Two G codes are used to specify circular commands. G02 specifies a clockwise motion, while G03 specifies a counterclockwise motion. As the name implies, this kind of movement will cause the tool to move along a circular path. And along with the endpoint for the motion, the size of the arc must also be specified. The control will cause the machine to move at the cutting feed rate, and feed rate can carry over from some previous G01 command. Circular motion is used for contour milling operations when machining radii.
Yeah, so feed rate is modal, so it can continue from a previous tool if it's the same feed rate.
It's quite easy to determine the difference between G02 and G03. Simply look in the direction that the tool is moving and ask yourself, is the motion a clockwise motion or a counterclockwise motion? If it's clockwise, you'll be using G02 for the motion. If it's counterclockwise, you'll be using G03. There are actually two ways of specifying the size of the arc that you're generating in the circular motion command. During this presentation, we're only going to be showing the method that uses the R word. The second method, using directional vectors, is presented in the student manual.
Do any of you that you're aware of have your machine requires using I and J and can't use R? No? Okay, good. There are some older machines that require using I and J. And what it is it's just the distance. It's an incremental distance from the start point to the center. But it creates way more opportunities to have mistakes. So the R is the way to go if you can do that.
The size of the arc you specify in a circular motion command must reflect the tool path that you are programming. If you're programming the centerline path of the tool, the R word must reflect the size of cutter that's being used. If you're using cutter radius compensation as discussed in key concept number 4 and programming the work surface path, then the R word will simply be the radius of the workpiece surface you're machining.
Does that make sense? I mean, because if I'm offsetting half the cutter and coming up with that number, I need to add that half a cutter to the radius too. Or if I'm on the inside, I would be subtracting.
Here is an example program that stresses the use of all three motion types discussed in this lesson. Note that a similar program is shown in your student manual. Since we are programming this tool's centerline path, the size of the R word must reflect the size of the cutter. Notice that we're adding the size of the arc we wish to generate to the cutter's radius. This renders the radius of the toolpath arc. Note that the R word is not modal. Even though the arc size in this circular motion command is the same as in the previous one, we must specify the R word in this command.
This is the end of this presentation.
All right.
Exit the presentation and read the document.
Okay. So I gotta stop sharing so I can come back. Does that kind of make sense so far, the motions? Okay. So I want to show you what I have in the Edmodo, I have put Haas G00 and G03. And what that is just Haas's recap of it. So there's some more information for you to go back and look at as we get rolling and trying to program and you're trying to remember a few things. So this has G00, G01, and the arc motions. It also explains if you have to use the I and J, like let's say you run into a machine that you have to do that with. The one thing they didn't point out that I want to point out is at the end of this document, and that is this. The R is always positive unless it is greater than 180 degrees. And then the R becomes negative. Does that make sense? So it's always going to be whether I'm going to the left, to the right, inside circle, outside circle, as long as it's less than 180 degrees, it's going to be a positive number, regardless of the size of the radius, as long as it's less than 100. A complete 360 arc using an R is not possible. The way you would do that is program 180 and then program another 180. And then you'll get your circle. If you're trying to circular interpolate a bore to try and work it out, there's some other commands that make that more possible within a CAN cycle. That would be the way to go. So I want to go, like as I said, here, we're going to go over the program structure, the Haas startup, and then the little program that I'm going to want you guys to make. But I want to go over cutter compensation because I want to teach you cutter compensation or cutter radius compensation. Depending on your machine, you might put your offset as a radius or as a diameter. Do you guys by chance know offhand if your mills do radius or diameter for the offset?
Diameter.
Don't know? Okay. So that, I mean, that's one thing you're going to want to know because if you go to setup, you need to know, do I put in my tool diameter or do I put in the radius of the tool? Okay. That's when it's going to matter. You're still going to program it the same way, regardless of how the machine deals with the offset. Okay. So I want to show you the next PowerPoint. The next one is much shorter than that one. And this is about compensation, not tool length compensation. We're doing Oh, this is intro to compensation. All right, so here we go.
In our discussion of machining center related compensation types by describing compensation from everyday life. You know, for example, that an airplane pilot must compensate when setting heading. A race car driver must compensate when negotiating a turn. And a marksman must compensate when firing a rifle. In all cases, compensation is required to allow for or deal with some unpredictable variable. In the case of the airplane pilot setting a heading, the unpredictable variable is wind. In the case of the race car driver, the unpredictable variables are related to
Can't see what the
I don't
presentation.
see anything.
the marksman firing a rifle. The unpredictable variable is the distance to the target.
Were you talking to me?
Yeah.
Yeah, it just shows you your file folder. It's just showing the file folder.
Yeah.
Okay, thank you. I forgot I have to like stop showing and then come back in and pick it again. How about now?
Now we're good.
Okay, I'm glad you said something. Otherwise, it would really be boring. More so. Yeah, it's really weird. Even though you're sharing and it switches and I can see it, if I don't stop sharing and then go and pick it, you don't get to see it. So, all right.
Before the marksman can fire a shot, they must judge the distance to the target and adjust the sight accordingly. And of course, the quality of their sight adjustment is going to be directly affected by their judgment of this distance. But even once the marksman adjusts the sight, they won't know for sure that their sight adjustment is perfect until they fire a shot. Once they do, the quality of their sight adjustment can be judged. Any error might be caused by an incorrect judgment of distance, but there may be some other unpredictable variable like wind that's affecting the quality of their sight adjustment. In any event, it's likely that further fine-tuning of the sight adjustment is going to be required to bring the sight right on the center of the target. Let's compare what you know about the sight adjustment to what a CNC setup person must do. Here's a sample workpiece that requires the machining of a pocket and the beginning of the related program. During the setup, a CNC setup person will do their best to measure and enter some tooling-related variables, like the tool's length and its radius. Just as with the sight adjustment, the quality of the workpiece is going to be directly affected by the setup person's ability to perform these measurements. Any incorrectness is going to show up right on the workpiece. And the setup person is not going to know for sure that this tool is going to machine the pocket correctly until the first workpiece is machined. After machining, they may notice some deviation from the desired or target size to the size that's actually being machined. This deviation may be caused by an incorrect measurement, or it may be caused by another unpredictable variable, like tool pressure. Either way, when critical tolerances must be held, it's quite likely that fine-tuning of the initial adjustment will be necessary. Just like any other form of compensation, all CNC machining center compensation types are designed to deal with or handle certain unpredictable variables. And the unpredictable variables are going to be related to either cutting tools or work holding tools. All compensation types also let the setup person enter compensation values separate from the CNC program. This allows the programmer to completely forget about the unpredictable variables that a setup person is dealing with compensation. In all cases, the programmer will simply include programming words and commands to invoke the compensation type. This will tell the control to look in certain registers within the CNC control to find the compensation value. And these registers are called offsets. Offsets are registers into which the setup person is entering the initial compensation value. It's also the register that they will use to fine-tune the initial setting. From the marksman analogy, you can think of the amount of sight adjustment as being like the compensation value a setup person will enter into the offset register. You can also think of offsets as being like memories in an electronic calculator. If you have a calculator that has, say, 10 memories, the memories will be organized by memory number. If you have a value that must be used regularly in a calculation, you can store it in one of the memories and recall it whenever you need the value within a calculation. Here we're looking at the first page of the tool offset display screen page on a typical CNC control. We must point out right away that offset tables vary from one control model to another. This is one style. In all cases, the offsets will be organized by number. And with this particular offset table, there is one value per offset. And you will always have a cursor that can be moved to any offset value for the purpose of offset entry. If, for example, I want to enter a value into offset number 14, I'll use the cursor control keys on the control panel keyboard. Once the cursor is positioned to offset number 14's value, I can type the value I wish to be placed in offset 14 and then press the input key. Note that most machine tool builders will equip their machines with an ample supply of tool offsets. This particular control has 99 tool offsets. Again, you must be prepared for variations when it comes to the offset table you have on your particular CNC machining center.
The Haas has that where they're separate.
Here is the first page of the Work Coordinate Systems display screen. Note that this page may be labeled differently from one control model to another. Here we're showing it as Work Coordinate Systems Offset. Most FANUC controls have 6 Work Coordinate Systems offsets. On the first page, we have the Common Offset and the first 3 Work Coordinate Systems offsets. The second page lets you enter 3 more offsets. Every print dimension has some kind of tolerance, whether it's explicitly specified or whether it's implied. A programmer must always program the mean value of the tolerance band. That is, the value that's right in the middle of the tolerance band. With a dimension specified as 3 inches, plus or minus 1 thousandths, program 3 inches. Again, right in the middle of the tolerance band. With the dimension specified as 3.004 over 3.002, program 3.003. Again, right in the middle of the tolerance band. Note that there is no exception to this rule. Always program the mean value of the tolerance band.
That helps give you some wiggle room.
Earlier, we said that a setup person is going to do their best to measure and enter certain tooling-related attributes. This implies that there's going to be some potential for error when it comes to how accurately they can enter these values. And as we've said, even if they enter the values perfectly, some other unpredictable variable, like tool pressure, will affect the quality of their initial adjustment. The tightness of your tolerance bands are going to determine whether or not the initial adjustment they make is good enough. With broad or wide open tolerance bands, the setup person will be able to make the initial adjustment in such a fashion that the first workpiece being machined will come out somewhere in the middle of its tolerance band. But the tighter the tolerance bands, the more likely it is that a setup person cannot make these initial adjustments properly. When milling this pocket, tool pressure may, for example, cause the end mill to push away from the surface being machined, causing the pocket to be machined undersized. Or the tool may be running out in its holder and machining oversized. In similar fashion, the tool may be pushing the workpiece away in the z-axis, causing the pocket depth to come out too shallow. Or it may be digging in and causing the pocket to be machined oversized. Whenever you're questioning whether or not the quality of your initial adjustment is good enough, there is a technique called trial machining that will help you ensure that the first workpiece comes out within its tolerance band.
This is one of those factors that you really can't predict. It's kind of like you find out after the fact, and that's why they're going to talk about this trial machining.
Trial machining involves making sure that your initial adjustment causes the tool to leave some excess stock on the surfaces being machined. Once machining has taken place under the influence of this initial adjustment, the workpiece will be measured to determine just how much excess stock there is on the workpiece. A second adjustment will then be made to make sure the tool cuts right in the middle of its tolerance band, and the tool will be restarted. The second time the tool cuts, it will cut within its tolerance band. We'll present more specific information about trial machining with each compensation type.
This is the end of this presentation.
Okay, let me stop sharing so you can see again. All right, so that's compensation, a little bit of each. What I want to show you now is some of the program structure. So we get away from the PowerPoints for a few minutes. I have one more about cutter radius compensation, but I want to show you a little bit about program format. Now I have put these in the Edmodo. Can you see Edmodo assignment?
Mm-hmm.
Okay, so I put the program structure, startup, and end lines. So let me open the program structure. Can you see program structure?
Yeah.
Okay, I just want to make sure that we're not. So what I've done is I've taken a few pages and made them smaller little documents from the big book, Haas programming book. They're all out of there. I just cropped them down to smaller so it's easier to find. So pretty much what, hold on a second. I had a better plan. So let me stop for a second and reshare. I can't annotate. Where is? All right, can you see program structure again? I'm sorry, yeah, program structure. I'm not sure if you guys know this or not. I just found this out. Normally I open a PDF and I use Adobe Reader. That's what I've always used. But if you're on a Windows computer and you open it with the Microsoft Edge, it has, you have the ability to do notes and draw on it. Are you able to see that I just drew on it?
Yeah.
Okay, I just want to make sure you're seeing the right one. Okay, so I can erase that. And the reason that I wanted to go to this one instead of the other one is because I wanted to point out that, remember, those of you who, all but one was with us for the lathe, we have to start our program with %. You need to have an O word, which is O and then 5 numbers. You always want to have in parentheses as comments. You want to put what it is, what's the program, what's your name, the date, revision number, any kind of important stuff. Like we're running this in a vise, you need to use 1 1/4 parallels. always ask Chilo for his 1/4-inch end mill. He's got a special one, whatever. Any kind of note. Because remember, I don't care if your boss tells you, we're never going to make this again. Okay? It never fails. 2 months down the road, it's going to be like, hey, remember that part you made? Knock me out another one. And if you don't have some kind of notes, you're going to be like trying to figure out what the heck you did in this program. Okay? So it's worth taking an extra 5 minutes and putting down and documenting some stuff. So these are some really important things in the beginning. And we've talked about this before, this safety line where I have, this is absolute, this is work offset 54, I'm going in rapid. I might want to put in G20 for American if I'm going back and forth between American and metric. I don't know what your needs are, but those default things that you want to make sure that are in place, you're going to want to put those on and a safety line, you know, before you actually go. I've said before that I don't approve, do what you want, but I don't like to put the spindle speed and tool on the same line as something else. It makes it harder to find. Typically, you do a tool change, and the next line after that is where you put your speed and turn the spindle on. Then make your XY move, then come down. Again, you want it to be clear so you can see it, and if you're the programmer sitting in the office, you want it clear for the guy out in the shop who's trying to figure this out, okay? It's a much better relationship if they don't think you're an idiot and you don't think they're an idiot. It just works a lot better that way, okay? I've worked with some programmers that I swear they got their jollies of trying to scare the crap out of us as operators, okay? Okay, I never found that to be that fun, okay? So this is kind of a sample of how they do things. Now I'm going to show you that there's 2 different ways when they go back for a tool change. When you're all done and you have to make a tool change, there's a couple of ways to do it. And this, what am I doing here? Press the button, I guess. This line right here, so these 2 lines are your typical lines to end and go to a tool change. I wrap it up above the part, I turn off the coolant. Now, you need to remember that M codes, miscellaneous functions, take place at the end of the line. Even if I move this M09 to the front of the line over here, it still won't be executed until the end. So if I send my Z all the way up to the top, you know, Z0 way up at tool change position and have the coolant come off on that line, it is not going to turn the coolant off until it gets all the way up, which means if you have a machine that doesn't have great guarding, you're getting a bath, okay? So you might want to make a shorter move, turn it off. So here, this line, they're using G28. You guys remember that from the lathe? What's G28?
Turn to home.
Return to home. So I return to home at an incremental distance, G91, of Z0 from home. Okay, so they're controlling that it's only a Z move at an incremental distance away from home of 0. Here's the problem with this, using this G91. If you don't have a safety line that has G90 in it, you're still an incremental, and every one of these XY moves is an incremental move. Things are going to get jacked up real quick, okay? So you may see this. This is one of the 2 ways you can go to a tool change, okay, or return to home. I'm not opposed to it, other than the fact that it makes it easier to go and forget about going back to absolute. And then I don't know where it's, you know, it's all incremental moves after that, okay? And then things are going to be all messed up. So I'm going to show you a method that I prefer, but neither are wrong. Does that make sense? So let me show you the one that I prefer. So this is the structure. Another document that I have is, I named it Mill Startup and End Lines. Okay. So here they're showing pretty much the same thing. They just didn't have their percent, their O word, and their comments before this. But they're doing a tool change. They're positioning X and Y. Then they're turning the spindle on. Then they're coming down. Let's see if this is LSR. Oh, you got tornado sirens? Okay. Yeah. Take shelter if you got tornado sirens. It's quiet here so far. So yeah, if that's the case, just let me know and go. So let me show you the ending lines. So here's the way I was just showing you, G28, G91. Okay, that's returning up. And this is explaining it. The other option is this right here. I can use G53. If you remember in our book, our work coordinate systems are G54, 55, 56, 57, 58, 59. G53 cancels the work offset, which means it's not relative to my program zero anymore. It's relative to the machine home. So what this is doing is turning off my work coordinate system, canceling my tool length compensation, because that was G43, sending it home. Okay, so I'm staying in absolute. Now when I do my tool change, all I want to make sure that I do is have my work offset again, and then I'll be good. Does that make sense?
Mm-hmm.
Okay. Like I said, both ways will work. I've just had some not fun days with incremental in the mills, so I had tried to avoid them like the plague. So this document is up there in the Edmodo for reference. Time is it 7:10? Okay. So what I would like to do, I gotta stop sharing so I can come back. What I would like to do is I would like you to go over the PowerPoint about cutter compensation, and then I want to show you a part that I want you to program. I'll show you the NC viewer first, and then I'll show you the part I want you to program. Really simple, but it'll get your feet wet. Okay, so let me first of all. Get this set up. All right, so. Okay, do you see the lesson 4.3? PowerPoint here? Okay. So this focuses on the cutter radius compensation. Let me ask you, are you guys kind of done with the PowerPoints for today, or can you do some more?
Doesn't matter to me.
Okay. I think it'll be helpful. I mean, because there's sometimes, when I'm going over it, occasionally I forgot stuff, and it makes it a little bit harder. So we'll go with this and get the gist of it. They do a fairly decent job of explaining it. So here we go.
As you know, tool length compensation is used for every tool in every program. The use of cutter radius compensation is not nearly so widespread. The only use for cutter radius compensation is for milling cutters, and when milling on the periphery of the cutter, as when contour milling. You will never use cutter radius compensation for tools that perform hole machining operations in a plunging fashion. Note that this includes times when using an end mill to counterbore a hole in a plunging fashion. We also recommend not using cutter radius compensation for face milling operations. Face milling is usually easier to accomplish when programming centerline coordinates. The first reason for cutter radius compensation applies most to manual programmers. The use of this feature will dramatically simplify the calculations required to come up with coordinates for a contour milling path. If you're not using cutter radius compensation for a contour milling path, the coordinates specified in the CNC program must reflect the tool's centerline path. This means, of course, that every positioning movement requires a calculation that takes into consideration the cutter's radius. The black dots represent the programmed coordinates, and the blue line represents the tool path. Note that for any circular motions, the specified radius must also reflect the tool's centerline path. When programming with cutter radius compensation, the manual programmer will position the tool to a convenient starting position. And at this position, we're still programming the tool's centerline location. During the command that actually inserts cutter radius compensation, the programmer will begin specifying coordinates right on the work surface. In essence, the control will keep the tool away from the programmed surface by the amount it sees in the cutter radius compensation offset, which will. Note that calculating the centerline coordinates for the previous example wouldn't be that difficult because all surfaces were at 90-degree angles. But programming the centerline path for this contour would be more difficult. The x-coordinate for this location, for example, would require some trigonometry, as would this y location. And the x and y location of this position requires some trig, as does this y location. Now, we don't mean to imply that using cutter radius compensation will eliminate the need for trigonometry. It will not. You may have to perform some trigonometry just to come up with the work surface path. But you should be able to see that trying to program centerline path requires much more in the way of manual calculations. Once again, with cutter radius compensation, the very first point programmed must take into consideration the tool's centerline position. But from here, we can program points right on the work surface. This truly minimizes the number of calculations required to come up with coordinates for the path.
Now, this is something that's key that after this, I'm going to kind of explain it. Think of it as you need an on-ramp and an off-ramp to execute, to instate and turn off the cutter compensation.
Cutter radius compensation will cause the control to keep the cutter on the left side or right side of all surfaces it sees from the first point. Keep in mind that this first reason for needing cutter radius compensation applies most to manual programmers. If using a CAM system to help them prepare programs, the CAM system can just as easily output a series of centerline path coordinates as it can work surface path coordinates.
Now notice they started with this cutter off the part and they finished it off the part. And that's a really important thing.
The second reason why cutter radius compensation is required applies to everyone, and most importantly to setup people and operators. Cutter radius compensation allows a range of cutter sizes to be used. If not using cutter radius compensation and programming centerline path, the setup person must use the size of cutter planned for. If, for example, the programmer specifies a 1-inch cutter, the setup person better use a 1-inch cutter. If they use a cutter other than the specified size, it will not maintain appropriate contact with the work surface. Note that once a milling cutter is dull, it must be sharpened, and companies like to be able to use their sharpened end mills in production again. The feature cutter radius compensation allows sharpened cutters to be used. The third reason why cutter radius compensation is required also applies to everyone, and especially to setup people and operators. Cutter radius compensation allows sizing and trial machining. The last reason we offer for using cutter radius compensation applies only to manual programmers. Cutter radius compensation allows the same series of coordinates used for finishing a workpiece to be used to rough the workpiece. This technique involves playing a trick on the control, telling the control that the roughing tool is actually larger than it really is. This will keep the roughing tool a specified distance away from the finishing path.
Does that kind of make sense to you guys? So let's say I'm only making one part. Instead of writing that path twice manually at the machine and keying all that in, I can just lie to the machine and say my 1-inch cutter's 1 inch 200 thousandths, and it's gonna leave 100 thousandths on a side. I can rough it out, measure it, adjust my offset again, and bring it into size instead of writing two separate tools. Now, if I was making a whole bunch of parts, that wouldn't really be beneficial. I'd be better off just copy and paste.
There are actually two ways of using cutter radius compensation. With the first method that we're going to be showing during this presentation and is also included in your student manual, the offset will be the cutter's radius, and the programmer will specify the work surface path coordinates. With the second method that's only discussed in your student manual, the offset value will be the difference or deviation from a planned cutter size radius, and the programmer will specify the centerline path for the tool. This second method is preferred most by CAM system programmers. With the method we recommend for manual programmers, you're going to be specifying coordinates right on the work surface. The setup person is going to specify in the offset the actual radius of the tool. If, for example, they're using a 3/4 inch diameter cutter, the offset value will be set to 0.375, that is half the cutter diameter. There are 3 steps to programming cutter radius compensation. The first step is also the most difficult, and it is to instate cutter radius compensation. After instating it, the programmer will specify the commands related to machining the contour. And when finished, cutter radius compensation must be canceled.
Now, this is the tricky part. When you instate it, you have to be far enough away so that when it fully is instated, because it kind of ramps and changes as it goes on that X or Y move or XY move, it doesn't really convert until it gets to that point. So you want to make sure you're off the part on that. See if they explain this.
The most difficult part of instating cutter radius compensation is determining a prior position that you're going to send the tool just before the instating command. And with this position, you must still specify the centerline coordinates for the tool. Say, for example, we wish to mill the left end of this workpiece. The tool path for this operation will look like this. We must first position the cutter a distance away from the surface to be milled that is at least the radius of the tool. I recommend using something that's a little larger than the biggest radius you expect your setup person to use. It's also important to instate cutter radius compensation so that when the tool begins cutting, a right angle is formed with the prior positioning movement.
Okay, so that's what's really important. If this tool radius plus the little bit more I do is not, it will limit how much of a adjustment I can make in my radius offset, okay, the tool radius offset. So what'll happen is, let's say I'm using a 1-inch cutter, so my radius is a 1/2 inch, and I only put in, I start my tool at 0.6 away. That really only gives me 100 thousandths of extra space. So if I were to say that my radius was 700 thousandths, when I tried to run it, it would come up with an error, okay? So I recommend leaving yourself some extra room on this ramp, so to speak, so that I can lie to the machine and say it's a couple hundred bigger if I want to use it for roughing and finishing, or I want some options. But that's really important, and that's where a lot of issues happen, where you'll come up with compensation error, or an error, or the program won't run because there isn't enough room based on that radius that's in the offset.
If, for example, you're using a 1-inch diameter end mill, the prior position must be at least a 1/2 inch away from the surface you intend to mill. By the way, this prior positioning movement also sets the maximum cutter size the setup person can use with the job. In our case, with our clearance of 600 thousandths, the maximum cutter size a setup person could use is 1.2 inches in diameter. Anything larger than this, and the control will think we're actually violating our first work surface prior to even instating cutter radius compensation. Here is the beginning of an example program that stresses how cutter radius compensation is instated. Notice that this is a 5/8 diameter end mill, and the setup person must store 5/16 of an inch in the offset related to cutter radius compensation.
Because it's radius.
Here is the prior positioning movement in X and Y. And notice that we're at least the cutter's radius away from the surface to be milled. And when we do start cutting, we're going to form a right angle with the first work surface. There are 2 G-codes used to instate cutter radius compensation. And the first thing a programmer must do is determine which of these 2 G-codes will be used to instate. G41 specifies a cutter left condition. G42 specifies a cutter right condition. We offer 2 methods for determining which of G41 or G42 you'll be using. First, look in the direction that the tool will be moving during its cutting operation, and ask yourself, is the tool on the left side or right side of the programmed surface? If the tool is on the left side of the machined surface, then you'll use G41 to instate. If it's on the right side of the machined surface, you'll use G42 to instate. The second method of determining which of G41 or G42 you'll be using assumes you know the difference between climb and conventional milling. If you're using a right-hand cutter and the spindle is running in the forward or M03 direction, G41 will be used whenever you're climb milling. G42 will be used whenever you're conventional milling. Notice that during the machining operation, the tool is on the left side of the work surface. Also, the cutter is climb milling. For these 2 reasons, we're using a G41 to instate cutter radius compensation. The offset is specified with D1. And also notice that we have moved the tool to the work surface of X0. The control will keep the tool away from this surface by the value it sees in offset number 1. Which in our case is 5/16 of an inch.
So just to be clear, that first position you went to before they instated the G41, you programmed to the center line of the tool, and it doesn't fully instate that cutter radius compensation until it gets to wherever the XY position is on the D01 line, where it picks it up, the G41 line. I have seen it at times on some machines if the distance isn't quite right, or if you go right to the line where it actually has moved the center of the tool into the part before it then shifted back out the radius. Doesn't typically happen, but it's a good reason to kind of stay off the part in one way or the other, or both directions.
Look in the direction of cut indicated on the diagram and determine the correct G code, G41 or G42. Click on the appropriate button to select your answer.
So is this G41 or G42, guys?
41.
Got a 41? It's 41. So they just got some quizzes. I don't think we need to do. Let's go here.
Within the instating G41 or G42 command, you will also include a D word to specify the offset number in which the cutter radius compensation value is stored. Which offset you actually use to instate cutter radius compensation will depend on the style of offset table your control has. If your offset table has 4 values per offset, as this table does, you should make the cutter radius compensation offset number the same as the tool station number.
Now remember, H is for height offset or the tool length, and D is for diameter or radius, depending on how the machine is. So this is showing 4. They have a wear for the length, and they have a wear for the diameter.
If, for example, tool station number 5 is a 3/4 inch diameter end mill, you'll store the radius of this cutter, that is 3/8 of an inch, in offset number 5's radius register. Remember that not all of the offset tables for FANUC controls have 4 values per offset. And if your control has but 1 value per offset, remember we've already used those offsets that correspond to tool station numbers for tool length compensation. We must use another method of determining the offset number for cutter radius compensation. We recommend adding a constant number that is greater than the number of tools your machine can hold to the tool station number to come up with the offset number used with cutter radius compensation. If, for example, your machine can hold 20 tools, then add 20 to your tool station number to come up with the cutter radius compensation offset number. With this method, tool station number 5 will use offset 5 for its length and offset 25 for its radius. The second step to using cutter radius compensation is to program the actual work surface contour. We do so with a series of simple motion commands, G01, G02, and G03. The third step to using cutter radius compensation is to cancel it, and the word G40 is used to cancel.
Typically, there needs to be some kind of a move, XY move, when you cancel, whether it be on that line or the next line. Otherwise, it doesn't always think that it went away until it makes a move. So in other words, if I put G40, didn't move anywhere, and then turn cutter compensation back on to make another pass around things, it might have an issue.
We recommend that whenever it's possible, after machining the contour, retract the tool in Z prior to canceling. It's been our experience that when machining multiple contours, beginners have a tendency of trying to do too much under the influence of cutter radius compensation. Remember that you must treat each contour independently, instate, cut, and cancel. If the tool must be positioned at rapid, it should be taken as a signal that you must first cancel cutter radius compensation before the rapid motion, and then move into the prior position for the next contour, instate, cut, and cancel. Here's an example program that uses cutter radius compensation to machine the left side of the workpiece.
All right, so this looks like we're repeating. So I'm going to stop here. And I kind of drew it up here, so I want to just review it really quick. Can you see a different screen now, a white screen with a...
Yeah.
Okay, so this is a part to just program, mill around the square, just kind of like we did. It has radiuses. The part that I'm going to give you, this is the part. I don't want you to worry about the radiuses. They're too small, because if a radius is on all four corners, that creates another nightmare of my in-state for cutter compensation that we're not going to deal with yet. So where do you think we should put 0 on this part? Or program 0 for X and Y?
The bottom corner left.
Bottom left corner would be a good choice. I mean, my dimensions are both coming from there, so that's where I would say yes. Okay. So I'm going to put my 0 in the lower left-hand corner. And I want to cut around in a clockwise motion. So I cannot just, oops, wrong thing. I cannot just take my end mill and just start here. Because if you look, there's this little, it would leave a little fillet, so to speak, this little radius here. You know, if I tried to do this, even if I came what I thought was the center line on line, I most likely will leave a little bit of a lip there. So I need to actually extend this line to come off the part. I have to create an extension to extend this down. So I'm going to start off the part and come up, go around and come off. And then if I'm going to put cutter compensation on, I have to have my ramp or my lead in so that I can come in. Does that make sense so far? So I'm going to position, and the center of my tool is going to come here to this position. And this is what they were talking about. The distance has to be at least the radius away. Plus, if I have stock on here, I have to worry about that too, maybe. If I'm making multiple passes, you know, I'm going to make I'm going to lie to the computer, or I'm going to do this twice so I can make a rough and a finish pass. I need to keep that in mind so that when I create this point, I'm far enough off the part so that when I wrap it down and feed into the part, I don't end up coming down on my part. So I position to here, and then what happens is as I tell it to go to this intersection right down here, it, by the time it gets there, will compensate and put the side of the tool there based on the radius number that I have in the, for the tool offset, for the diameter offset. But I'm going to program the center point here, and then I'm going to go to this point. I don't have to stop here because there's no reason to stop. I just extended the line. So my next line, I would program all the way up to this corner right up here, the upper left-hand corner. Then I would program to the upper right-hand corner. I would come down to the lower right-hand corner, and I wouldn't stop here. I would continue off the part. So what I'm doing is this. My part is driving around like this, and I'm coming off. When it stops, it's always tangent to the center line. So that's how I was able to determine to stop here. It's pretty close to tangent. So wherever the center line is, it's going to be tangent to the end point of that line. So I need to make sure I do some math and make sure that this is off the part. Does this make sense? Okay. So when I'm positioned here, I G00, wrap it here, Z, come into what depth I want. This line here is my ramp, which is where I'm going to put on G41. It comes into effect here. When I come around and I come off of here, this is when I'm going to then, after I get to this point, the next line is when I'm going to do a G40 to cancel this. If I were to cancel here, if I gave it this X position and said G40 and this X position, here's what would happen. Watch what happens. As it's going along, it's gradually ramping down so that when it gets to this point, cutter comp is off. So I just cut an angle on my part like that. If I make the G40 cancel on the line that makes a move. Does that make sense?
Mm-hmm.
Okay, so I don't want to do that until after. So I want to get here, then I want a G40 cancel. I can make a move right back down here if I want to turn it off. I could come back to my same start point because I know where that is on my turn it off. So that's kind of the game plan here. Okay, questions? Okay. Have you guys done this before with cutter comp?
A little bit.
A little bit? Okay. So, but you're okay with it? It seems to make sense so far? All right, so let me show you just a little bit more. I want to show you the part you're going to program, where we're going to put 0, and then I'm going to show you the NC viewer, and then that'll be it for today unless you guys got questions or want to see something else. So let me go to share the screen again. And where is it? Can you see this part? A part
Yeah.
that says Titans? Okay, so I just took this part. If you guys are doing anything with CAM programming or whatever, this Titans of CNC, it's free. You just got to make an account. And they have lathe parts. They have mill parts. They go through step by step. They use Fusion 360 for how to program. They also have Mastercam now for some of their parts, where they show you how to program it with Mastercam, but they actually show you step by step. So that's where I got this part from. This is one of the parts. So this is what we're going to do. I'm going to want you to write a program. Let's put 0 in the lower left-hand corner. Let's use a 1/2-inch cutter. And I'll add that to the notes in the Edmodo, because I didn't pick a cutter size. So if we use a 1/2-inch cutter, so I'm going to want you to do pretty much just like I just showed you. You're going to start over here, off a safe distance, come in, go around, come off, turn off cutter compensation, so that you could mill this size. Okay, let's just do one pass around. Make sense?
Mm-hmm.
Okay, I guess I gotta unshare so that I can reshare. I want to show you that programming thing. Let's see, I think this is where I wanna go. So it's ncview, VIEW.com. Nope. Oh, NC Viewer. My bad. Do you see NC Viewer on the screen?
Mm-hmm.
Okay. I wanted to make sure you're seeing what I'm seeing. So this will allow me to do this plot Z up. This will do mill. It'll also do lathe. Turn that off. Here's a sample. So this sample, if I pick in here and I just arrow down, it will drive my tool around and show me where it is on the part. So I can actually see the path, just like we could on the simulators at TMA. Okay. It works the same way. I can pick up here and start a new file. And I'm going to start with my %, and you're just going to type it in. Then I'm going to have the O word. And then I'm just going to continue on with comments, and I'm going to write the program just like we did on the simulators at TMA. Okay. Use those documents in that I have in Edmodo to support so that you have the right start, that you do a tool change. Let's say it's aluminum. I don't remember what the document said, but let's go with RPM and a feed rate for aluminum, figure something like that out. Doesn't have to be perfect. I really just want you to kind of get the idea. So what I'm going to want you to do is when you have a program, I want you to save the program because you can save the file. And then I want you to turn it into the assignment for today. It doesn't, and doesn't have to be today. Just turn it into that assignment. And then I can open it up and I can pull it in here and I can view it and see what you got. So if you have problems, you could send me the file, let me know that you turned it in. I can look at it and I can give you guys some feedback about where you're having problems if you're having problems. Okay? Questions?
Mm-mm.
All right, so I will add a note that says we're going to use a 1/2-inch cutter. So actually the link, I believe, let me stop sharing this and I'll double check. Let's go back to Edmodo. On the Edmodo screen, yes, there's a link for it right here. So if you pick this link right here, it'll launch it. Right above it is the print Titan 1M. And again, these documents are here for you to reference, whether you want to print them out or just leave them digitally, that doesn't matter to me. So we're going to use a 1/2-inch cutter and try and see if you can make that program. And then before class, preferably not later than Monday, give me a chance to look at it. Send it to me and, turn it in here. When you do the assignment, you have a chance, a place to turn it in. Since I'm the teacher, it doesn't show me here, but it does send me a note that says that something was turned in. So then I'll look at it, and if you guys need some help, I will try and fix that up. Okay. So I don't have anything else. If nobody has any questions, then we can call it a day, and you can use some of this time to probably knock out that program before class would normally be over. All right. And again, I'll be on board so that if you got questions in a little bit, I'll just let me know. Shoot me a text if I didn't catch it in the email or whatever, and we can try and get connected up and get you set up. Okay.
Okay.
All right. Now, Chilo, are you okay with the Edmodo?
Yeah, I think so.
You can get in there and see it?
Yeah.
Okay, okay. So like I said, if you guys get stuck or something, shoot me a text and we'll get it straightened out, okay?
Sure, okay.
All right, so I'll be looking for your programs and then we'll connect up again on Tuesday.
Okay.
All right, take care.
Thank you.
All right.
All right.